Simultaneous determination of reservoir pressure in a multi-well system. I have 18 years experience in oil and gas industry. Today, I'd like to introduce a new method to determine average reservoir pressure. Introduction. One frequently encountered in difficulty in artificial lift workover is lack of shortening reservoir pressure. We usually don't have enough time to get the build-up pressure that is unrealistic for each well, each workover. So we need to determine the average reservoir pressure in an easier way. This work presents a method that can be applied under pseudo-steady state conditions to simultaneously determine the average reservoir pressure around well bores using only surface production data and pump intake pressure. As we all know, if the average reservoir pressure is not accurate, this could lead to the improper design of ESP and other artificial lift tools. Usually, we have experienced one case in our field, that is well 5. In that time, the average pressure is overestimated and the productivity index is much higher than realistic. That caused the loss of money and redesigned the ESP. So to calculate the average reservoir pressure correctly is very important. Objective is to present detailed mathematical evaluation of a method, which can be used to simultaneously determine average reservoir pressure around a well wall in reservoirs without relying on pressure build-up tests. Procedures. First, calculate reservoir pressure through dirt pressure divided by dirt cumulative fluid, that is cumulative oil and cumulative water. Second, collect production data. This includes the oil, water production, and pressure. Third procedure, generate reservoir pressure profile using pressure buildup result. Fourth, dynamic reservoir pressure through pressure profiles in a multi-well system. Fifth, calculate productivity index and calibrate using steady state periods. Sixth, forecast dynamic reservoir pressure using the productivity index and other data. Charter legend. Orange represent data collection phase. Blue is data analysis phase. Green is the forecast phase. Here is the reservoir pressure dynamic prediction methodology. First step, data collection. The proposed approach uses base reservoir pressure survey data along with the corresponding historical production data to estimate the reservoir pressure for a key well. Detailed steps are outlined as following. First, data collection. The methodology starts with conducting the base flowing pressure survey to measure the pressure at the intake of the ESP. This pressure is then corrected to the reservoir pressure at the mid-perforation using oil and water gradient and BSW percentage. Fluid gradient in wellbore is dependent on the BSW and oil gradient as follows. When the BSW is low, fluid columns in the wellbore is assumed to be oil. In this case, we can use oil gradient. Otherwise, fluid gradient equals BSW plus 1 minus BSW times oil gradient, then times water gradient. Here, water gradient equals 0.433 psi per feet. So, if we have the intake pressure of the pump and the BSW percentage and the dirt height between the middle perforation of the reservoir and the intake of the sensor ESP, then we can calculate the flowing pressure at the mid perforation. The equation is as following. Flowing pressure at the middle perforation equals intake pressure and BSW, the fluid gradient, times the dirt H between mid perforation and intake sensor. After calculating the mid-perforation reservoir pressure for the targeted well, relevant well's performance data are collected as follows. Surface production data, such as oil rate, liquid rate, water cut, and the flowing wellhead pressure or the intake pressure. Pressure volume temperature data, such as formation volume factor and the solution gas oil ratio. Bottom hole flowing pressure data at the intake of the ESP. Well completion dimensions. Build-up test recordings. Latest pressure transient analysis, if there is any. Second, generating reservoir pressure profile from build-up. At least one reliable pressure build-up test is needed to generating reservoir pressure profiles. Here, the build-up should be representative. In the best case, the build-up test should from the first well in the block, which would be representative. Predictions performance analysis is conducting using the following data. First, ESP intake pressure recordings during buildup. Second, wellhead flowing pressure. Third, reservoir drainage area estimation. Here, for vertical well, without fracturing, the pressure spreads afterwards in a circle on the plane, and the pressure spread radius satisfies the following equation. R in V equals 0.5879 square permeability times divided by porosity times viscosity times compression factor. Here are investigation is circular investigation radius. Here is meter. T is the time in days. K is reservoir permeability in millidecade. Phi is reservoir porosity. Mu is formation oil viscosity. Ct is compression factor. Generating reservoir pressure profile from pressure buildup. If we have a pressure buildup result, that is a representative one. In here we have the pressure buildup in a long time and get a stable status. That means the final pressure becomes stable. Then in a reservoir with aquifer, we can assume the final buildup pressure equals the pressure near the aquifer. From the pressure recording, we know the pressure near the well wall, and we know the times of the buildup. Using this equation, then we can convert times to the length near the well wall. Then we can generate a profile, pressure profile near the well wall along until the aquifer. Third procedure, productivity index analysis. Liquid flow rate, water cut, and flowing pressure data are statistically analyzed to select three representative data sets. Representative data needs to satisfy three conditions. First, it should have constant production rate. Second, analyze intake pressure to define their normal variation and detect possible outlying data points due to abnormal well behavior or erroneous measurements. This data we should delete. Third, a representative reservoir pressures. Here is the intake pressure. Then we can calculate the productivity index that equals flowing rate divided by the delta pressure between reservoir and the middle flowing pressure. By invoking the assumption that each well's productivity index keeps consistent, we can back calculate the reservoir pressure. In case of any change on productivity index, such as sand plugging or cleaning, we need to recalibrate well's productivity index and repeat these steps. In order to eliminate the uncertainty in the well's productivity index calculation, at least 3 data sets are recommended. Fourth procedure, dynamic reservoir prediction. After generating and calibrating the well performance, future reservoir pressure values are calculated from ESP intake flowing pressure as following. At a given flowing rate, bottom hole flowing pressure at the middle perforation is back calculated using the hydrostatic pressure gradient and BSW. Using the calculated productivity index value in section 3, reservoir inflow performance relationship is used to back calculate the reservoir pressure. Reservoir pressure equals flowing pressure plus flowing rate divided by the productivity index. This procedure is repeated for all wells. Whenever key well is closed again, then recalibration is recommended to evaluate the well performance model following the steps in the section 3. Here, I'm going to introduction a field application and a prediction performance analysis. In this part, example of 4 cases study from the same sand reservoir is presented. These case studies were deliberately selected to represent all ranges of operating parameters and the reservoir pressure. In the V field, this is the structure map of the G reservoir. Here we have 4 wells, well 3, well 5, well 7, and well 9. The correlationship is like this. Well 5, well 3, well 7, and well 9. In this direction is the northwest connected to an aquifer. So here is the aquifer supporting the reservoir pressure. Let's see the first well, well 5. Well 5 is the first oil producer in V field. 2 years later, after producing, a pressure buildup was conducted. The objective of the test was to record bottom hole pressure and temperatures in the well during 6 straight days of shut-in pressure buildup test. After being produced for 2 years, that is 719 days of the intervals 11,810 feet to 11,818 feet in the middle, measured depth, and 11,821 feet to 11,837 feet in measured depth of the sand formation. The analysis of this information seeks to determine reservoir pressure, estimate reservoir properties and well conditions, like the reservoir permeability, formation damage during the production period, estimate the productivity index, identify and characterize flowing barriers and or reservoir boundaries like the force, stratigraphic boundaries, aquifers, which will reduce uncertainty about the reservoir size, reserves, and additional drainage points. This is the mechanical status of well 5. This is the ESP. The sensor is installed here, and the measured depth is 9,614.4 feet. In TVD is 8,899 feet. Perforation depth 2 layers. First is around 11,818 in measured depth, and the second perforation is around 11,837 feet. So we can calculate the middle perforation to the sensor and then calculate the gravity between the sensor and the middle perforation. The produced oil has 14.8 API. The production water has a chloride content of 452 ppm, which is typical of the sand formation. According to the pressure measured by the sensor in the ESP and static conditions prior to start production is 3,863.7 psi. A static reservoir pressure of 4,433.6 psi at the middle perforation was estimated. This value is in accordance with the measured pressure in the wells of V field. Here, a flowing gradient of 0.4184 psi per feet was assumed. Based in vertical flowing correlations of the pipeline estimated from a nodal analysis. The pressure in the middle reservoir equals pressure of the intake plus the delta P between sensor and the middle perforation. That is, however, we need to keep in mind that this recorded initial static reservoir pressure could be not accurate if control fluid gradient exceed the static hydraulic gradient. This is a common case, especially in the first well. The drilling and workover team usually use the control fluid gradient a little larger than the static hydraulic gradient to keep the drilling and workover activities to be safe enough. Production behavior. The well 5 once completed on July 2014 started with an average fluid production of 400 barrels per day. It's really stable. By the end of July 11th, 2016, a cumulative of 364,109 barrels fluid was produced. This is the oil and water production. Here is the BSW remains quite slow, basically zero. And this is the gas production. In the bottom, the red line is the intake pressure of the sensor. The blue line is the ESP frequency. So during this period from 2014 to the 2016, both the flowing rate and the frequency kept quite stable. Pressure build-up test. A very stable flow rate was observed with an average value of 489.7 barrels per day, with little variation in the bottom flowing pressure values, which at the shut-in time was in the order of 2,369.7 psi at the center depth. The bottom flowing pressure before closing the well was 2,369.7 at the sensor depth, which is equivalent to 2,939.6 psi at the datum depth. On July 11, 2016, the well was closed in service for 1,528 hours. That is almost 64 days, with a recorded sensor pressure of 3,433 psi at the sensor depth. which is equivalent to 2002.98 psi at the mid-perforation depth. Reservoir pressure profiles around well 5. After nearly 64 days, the bottom pressure tends to become stable. Here, invoke the assumption that the final build-up pressure equivalent to pressure close to pressure of the connected aquifer. The aquifer here is around 1,200 meters away in the V field case. Because the build-up lasts long enough time is nearly 64 days. At the later stage, we can notice the pressure in the intake pressure becomes quite stable. If we extrapolate the trend, the final pressure could increase a little bit, but that would take a much longer time using the well tested result. And we know that the aquifer, the pressure in the aquifer almost keeps the original. So we can reasonably assume the final pressure of the buildup equals to the pressure in the aquifer. And then we know the pressure near the wellbore and the times of the recovery. For vertical well without fracturing, the pressure spread afterward in a circle on the plane, and the pressure spread radius satisfies this equation. So in this pressure buildup, we recorded the time and the pressure at each time. Then we can convert the time into the investigation of the radius. Using the equation, we can generate the pressure profile from the wellbore to the aquifer. So here, at this point, we recorded a pressure in the wellbore, and this is the pressure at the aquifer. This is the delta pressure between the wellbore and using the pressure build-up time, we can get this pressure profile of the well 5. So basically, we get the pressure here. We know the pressure in the aquifer. We know the time it takes and the final pressure of the build-up. We can generate the pressure profile between well 5 and the aquifer. from this pressure profile, we can see the closer to the well bore, the delta pressure is larger. Initial reservoir pressure calibration. Previously, we introduced that the static pressure before start production is 4,433.6 psi. As we noticed, this number could be not accurate because of the control fluid gradient problem. So we need to calibrate the initial reservoir pressure. The procedure are as following. We are going to introduce the pressure decline per cumulative fluid, that is the dP divided by dNP. NP is the cumulative produced fluid. Since our main objective is to determine initial reservoir pressure, two parameters need to be determined. The first one is a representative delta P divided by delta NP, which usually present in a consistent rate period. Second, delta P between the flowing pressure hole, bottom hole pressure, and average reservoir pressure. Here, we assume this delta P is similar to the delta P between flowing pressure at the start of the buildup and the pressure at the end of the buildup. The pressure, initial pressure equals intake pressure plus gravity delta P plus the pressure caused by the produced fluid plus the delta P of the buildup. In valve 5 case, we finally calculate the initial reservoir pressure is around 4,281 psi. So we compare these two initial pressure. Static pressure measure is 4,433.6 psi. And the second method is using pressure decline per cumulative fluid. Back calculation, we get the initial pressure is 4,280.9 psi. So the difference between these two methods is around 150 psi. And as we introduced in the first slides, the static pressure measurement could be not accurate. It's usually a little higher than the reservoir pressure. So here we believe the V field G formation, the initial reservoir pressure is around 4,281 psi. The second procedure is to calculate well 5 productivity. As we introduced in the mechanical status slide. The flowing pressure at the middle perforation equals intake pressure plus the gravity pressure. So for the first 3 points, PIP 3024, we can get the flowing pressure at the middle perforation 3,604 psi. That P is around 580 psi. So for each PIP, we can, using the BSW on the dart H, then we can get a corresponding flowing pressure. Here we ignore the friction of the fluid during the production, since here the flowing rate is not quite high. Calculate productivity. The productivity index equals flowing rate divided by the delta P between reservoir pressure and the flowing pressure. Here the initial pressure we are using 4,281 psi. Then using the first flowing rate, we can get the PI is around 0.458 barrels per day per psi. As we introduced before, the productivity index is very important to back calculate the reservoir pressure. So we need to double check and calibrating this PI. The methodology is as following. Liquid flowing rate, water cut, and flowing pressure data are statistically analyzed to select 3 representative data sets. Representative data needs to satisfy 3 conditions. The first, consistent production rate. Intake pressure to determine their normal variations and detect possible outlying data points due to abnormal well behavior or wrong measurements. Representative reservoir pressure. Here we select 3 periods. The first one is from the 2014 July to 2017 November. We can see the production rate keeps stable. It's around 406 barrels per day. The pink is the frequency of ESP. It keeps at 49 Hz. And here we need to define the correct intake pressure. The second period is from the February of 18 to the January 19. The fluid is around 6 barrels per day, and the ESP frequency is at 43.5 Hz. Then a consistent period is from June 2022 to the April 2023. Flow rate keeps at 290 barrels per day. Frequency 45 Hz. And the intake pressure keeps stable with a slightly decline rate. In each of these three selected periods, statistical analyze the following. First, calculate the delta P per delta cumulative fluid. Re-estimate average reservoir near wellbore. Calculate PI for each period. So for the first period, we calculate the delta P of the intake pressure of these two dates. The PIP delta P is 313 psi. The delta cumulative produced oil and water, we can get the dP divided by the dNP is 0.559 psi per 1,000 barrels. Using the dP dNP, we can calculate the current average pressure, and then using the flow rate divided by the delta P between P average reservoir pressure and the flowing pressure, we can get the PI in these two dates is nearly 0.5 BUPD per PSI. In the 2018 February and November, the delta P is 64 psi. dP per dNP is 0.388 psi per 1,000 barrels. Then we can calculate the current average reservoir is nearly 3,790 psi, and the PI using the same methodology is 0.5 BUPD per PSI. Let's compare this PI with the PI we calculate from the first point, that is 0.458. So these PIs are quite close. So we can see this PI, the first PI could be representative to calculate the back calculated reservoir pressure. Okay, the third procedure is to back calculate the dynamic reservoir pressure around well 5. The equations are reservoir pressure equals flowing pressure plus the flowing rate divided by Pi. Here we are using 0.458 barrel per psi. So here is we are using the PIP, that is the intake pressure, BSW, and the delta H between middle perforation and the sensor, and then the flowing rate of each state divided by the Pi. Then we can get the dynamic average reservoir pressure around well 5 well bore. Here is the green line. We can see currently the average pressure is around 2,500 psi. So for each intake, we can using this method to stimulatorily calculate the average reservoir pressure around the well bore. This is the well 9 case. Well 9 is the second oil producer in V field, which was put on stream on November 2018. The location is here. This is the well 5. Well 9 is away from well 5, around 460 meters. Procedures to calculate well 9 dynamic reservoir pressure as following. First, determine initial reservoir pressure at the start of production. We can use the flowing pressure of well 5 at the start of production of well 9. Then calculate the delta P between flowing pressure of well 5 and average reservoir pressure around well 9, which is determined through well 5 pressure buildup reservoir pressure profile. Then calculate well 9 productivity, and then back calculate the dynamic reservoir pressure around well 9. Step 1. Determine initial reservoir pressure near well 9 well bore at the start of production. Flowing pressure of well 5 at the start of production of well 9. Well 5 well test on November 2018. The oil rate is 567 barrels per day, water rate 11 barrels per day, so the BSW is nearly 1.9%. The intake pressure is 2085 psi. Pump intake TVD is at 8,899 feet. Mid perforation at 10,283 feet TVD. So we can calculate the flowing pressure at the middle perforation by this equation. using the intake pressure, gravity between sensor and middle perforation. That is 2,655 psi. So flowing pressure of well 5 at November 2018 is 2,655 psi. That is the well number 5 flowing pressure. Then calculate the delta P between well number 5 and well number 9. Well number 9 is away from well 5 around 460 meters from the well number 5 pressure profiles. A delta P of 6,085 psi between flowing pressure of well number 5 and average reservoir pressure around well number 9 is assumed. Here, well number 5, well number 9 is 460 meters away. So we get the delta P is 885 psi. So we can get at the start of the production the well number 9 average pressure, reservoir pressure equals flowing pressure of number 5 plus the delta P, that is 2,655 plus 685 equals 3,340 psi. This is the initial average reservoir pressure around well number 9 well bore. Step 2. Calculate well number 9 productivity index. This is the mechanical status of well number 9. The sensor TVD is at 9,032 feet. The perforation, middle perforation, is at 10,332 TVD feet. Using the intake pressure and BSW and the delta H between middle perforation and the sensor, we can get the PIP and the flowing pressure for each node. PI, productivity index, equals flowing rate divided by delta P between reservoir pressure and flowing pressure. In the step 1, we calculate the initial average reservoir pressure around number 9, well number 9, well bore is 3,340 psi. From the intake pressure, we get the flowing pressure, and then we calculate the initial productivity index is 5.1 97 barrels per day per psi. Where 9 productivity index calibrating. So we'll select another 3 period with consistent production rate, reasonable intake pressure. The first period is from the middle of 2019 until the middle of 2021. Here, the fluid rate is around 450 barrels per day. Intake pressure declines steadily. Second period is from April 2022 to August 2022. Flow rate 460 and intake pressure here, and the ESP frequency keeps consistent. Finally is the period in March 2023 to June. In this period, the BSW is around 13%. ESP frequency is at around 51 Hz. So from 2019 to 2021, the delta P of the intake pressure is 175 psi. Delta P per delta MP is 0.582 psi per 1,000 barrels. Using the initial pressure, we calculate the average reservoir pressure around wellbore is 3,177 psi and 3,002 psi representatively. And the productivity index is around 5.9 to 6.3 barrels per day per psi. In 2022 production period, the delta P is 32 psi. Delta P per delta cumulative fluid is 0.4 psi per 1,000 barrels. We calculate the average reservoir pressure near the wellbore is 2,888 psi and 2,856 psi representatively. And then the PI is 6.9 to 6.1 barrels per day per psi. We compare these numbers, PIs, with the initial PI, that is 5.2. So this is relatively a little lower compared to the number in 2022, but more close to the PI in the calculated in the 2019. Step 3. Back calculate the dynamic reservoir pressure around well 9. Here, the PI we using the initial, that is 5.9 barrels per day per psi. We calculate this is the dynamic reservoir pressure around well number 9, the ground one. Currently, it is nearly 2,550 psi. The third well number 7. Well number 7 is the third oil producer in this field. It is in the middle of well number 5 and well number 9. Well 7 was put on stream on April 2019. It is away from well number 5 around 240 meters. Procedures to calculate well number 7 dynamic reservoir pressure as following. First, determine the initial reservoir pressure at the start of production. We are using the flowing pressure of well 5 at the start of production of well 7. Delta P between flowing pressure of well 5 and average reservoir pressure around well 7, which is determined through well 5 pressure build-up reservoir pressure profiles. Then the well 7 productivity index calculation. Then back calculate the dynamic reservoir pressure around well 7. First, determine initial reservoir pressure near well 7 wellbore at the start of production. Flowing pressure of well 5 at the start of production of well 7. Well 5 will test on April 2019. Oil rate 532 barrels per day. Water rate 11 barrels per day. BSW 2%. Intake pressure 1,931 psi. Pump intake at 8,899 feet TVD. Mid perforation at 10,283 feet TVD. So we can calculate the flowing pressure at April 29 using the equation that is 2,510.9 psi. Delta P between well 5 and average reservoir around well 7. So well 7 is 240 meters away from well number 5. From this pressure profile, we can get a delta P of 410.1 psi between the flowing pressure of well 5 and average reservoir pressure around well 7 is assumed. So the dynamic average reservoir pressure around well number 7 is the flowing pressure of well 5 plus the delta P. That is 2,921 psi. This is the average reservoir pressure, initial reservoir pressure around well 7 well bore. Well 7 mechanical status. The sensor is put at 8,918 feet TVD. The mid perforation is at 10,308 feet TVD. Then we could get the delta P between sensor and the middle perforation. PI. Here, the initial reservoir pressure we are using 2,921 psi. Then we can calculate the initial productivity is 0.778 barrels per day per psi. This is the average. Now we select another three consistent producing period. The first is from July 2019 to November 2020. The flow rate is at 460. ESP frequency keeps consistent at 55 Hz. Intake pressure consistent and with a slightly decline rate. Second period, from July 2021 to January 2022, flow rate consistent, and ESP frequency at 56.5 Hz. Intake pressure stable and decline. Third period is from March 2023, when the water coming with a production rate around 500 barrels per day. ESP frequency keeps at 57 Hz. So for the first period, the delta P is 121 psi, delta P per delta MP 0.546 psi per 1,000 barrels. So we can calculate the pressure at 2019 August 4 is 2,845 psi and 2,724 psi at December 2020. Then we calculate the PI is 0.8 to 0.75 barrels per day per psi. In the second period, the delta P is 59 psi, delta P per delta MP 0.97 psi per 1,000 barrels. Then we calculate the reservoir pressure around 2,545 psi and 2,486 psi representatively in 2021 July and 2022 January. The productivity index is 0.768 and 0.746 barrels per day per PSI representatively. So let's compare these PIs with the initial one. The initial productivity index is 0.778. This is quite close, except this number. So we think the PI, representative PI, is around 0.75 barrels per day per PSI. Back calculate the dynamic reservoir pressure around well 7. The reservoir pressure here equals flowing pressure plus flow rate divided by the PI. Here, the PI we are using 0.778 barrels per day per PSI. So, using this equation, we back calculate the average reservoir around well 7 well bore. The grand point represent. So currently we estimate the reservoir pressure around well 7 is around 2070 psi. Why? The pressure declined and then increased. That is related to the aquifer. From the production chart we can see from the beginning of 2022 the water comes and the current BSW increased to 7 to 12%, and that contributes to the buildup of the pressure. Okay, let's went to the well 3. Well 3 is in the other side of the well 5. Well 3 is the fourth oil producer in V field, which was put on stream on May 2019. Well number 3 is away from well 5 around 206 meters. Procedures to calculate well 3 dynamic reservoir pressure as following. First, determine initial reservoir pressure near well 3 at the start of production. Calculate well 3 productivity index. Back calculate the dynamic reservoir pressure around well 3. This is the production chart. You may be puzzled why the well number 3 is at the highest of the structure, why the BSW is higher than the previous wells. Okay, here the BSW could be related to the leak of another well produced in another formation. That is caused by the poor cement. This is confirmed by the chloride or salinity of the produced water. Step 1. Determine initial reservoir pressure near well 3, well 4 at the start of production. Fluid pressure of well number 5 at the start of production of well 3. Well 5 will test on May 2019. Oil rate 532 barrels per day. Water rate 11 barrels per day, so the BSW 2%. Intake pressure 1793 psi. So using the equation, we can calculate the fluid pressure of well 5 at the May 2019 is around 2372.9 psi. Delta P between fluid pressure of well 5 and average reservoir pressure around well 3, well 4. So well 5, well 3 is 206 meters away from well 5. From the well 5 pressure profile, a delta P of 310.1 psi between the fluid pressure of well 5 and average reservoir pressure around well 3 is assumed. So the average pressure around well 3 equals fluid pressure of well 5 plus the delta P 310. That is 2683 psi. This is assumed as the average pressure around well 3, well 4, initial pressure at the 19th May 2019. Mechanical status of well 3. The sensor is put at 8,546.4 feet TVD. 2 perforation layers. The mid perforation is at 10,257 feet TVD. So the gravity between sensor and the middle perforation is around 700 psi, depending on the BSW percent. Productivity index equals fluid rate divided by the delta P between initial reservoir pressure and fluid pressure. Then we can get the initial productivity index around 0.327 barrels per psi. Here we are using the initial pressure of 2683 psi. PI calibrating. Select 3 consistent production rate period. The first one is from August 2019 to September 2020. Fluid rate at around 250. ESP frequency at around 59 to 60 Hz. Intake pressure slightly decline. Second period, July 2021 to January 2022. Flowing rate is around 300 barrels per day. ESP frequency 61 Hz. Intake pressure slightly decline. Third period, from July 2022 to the end of 2022. Flowing rate 300 to 290 barrels per day, with a BSW of 15%. ESP frequency 43 Hz. Intake pressure slightly decline. In the first consistent producing period, the delta P is 130 psi. Delta P per cumulative fluid 1.436 psi per 1,000 barrels. Average pressure near the wellbore. On the October 25th, 29 is around 2,629. October 2020, 2,499 psi. Then we can calculate the PI is around 0.3 to 3 barrels per day per psi to 0.3 barrels per day per psi. From the June 2021 to January 2022, the delta P is 157. Delta P per delta cumulative fluid 2.55 psi per 1,000 barrels. So the average pressure around the wellbore is 2,342 psi and 2,185 psi representatively at this to date. And PI is around 0.358 psi barrels per psi. Let's compare these PIs with the initial PI. The initial one is 0.327 barrels per day per psi. So these numbers are quite close. We think the initial PI could be representative for well 3. Step 3. Back calculate the dynamic reservoir pressure around well 3 wellbore. Reservoir pressure equals flowing pressure plus flowing rate divided by the PI. Here we are using 0.327 barrels per day per psi as the representative PI. For each production node, we know the BSW, we know the intake pressure, then we know the representative PI, we know the flowing rate, then we can back calculate the dynamic reservoir pressure around the wellbore. So from the initially 2,700 decline to the currently 2200 psi. Summary. If we combine these four wells, back-calculated dynamic reservoir pressure around the well bore, we can get this chart. This is the initial well number 5, the initial well. We can see the area reservoir pressure steadily decline. When other wells comes, it drops dramatically because of the drawdown. Then we can see these three wells. This is well number 9, number 7, and number 3. Well number 9 well number 9 is close to the aquifer, then number 7, then number 5. Then the well 3 is far away from the aquifer, so the area reservoir is the lowest among these four wells. This is here. Well 9 close to the aquifer and the pressure is highest. Well 3 is the far away from the aquifer and the area pressure is the lowest. So this looks reasonable using the PI back calculation methodology. Field application. Application 1. Using the back calculated drawdown and evaluate the risk of sand producing. Well 7 sand production. Since the second quarter 2023, sand production exceeds 3 ppb, that is pound per barrel, whereas only 0.2 ppb previously. So we want to calculate the crucial drawdown pressure and to avoid sand production. So at this point, the sand production increased dramatically. We think the drawdown at this period is crucial. That is the maximum drawdown. Before sand producing. The procedures are as following. With the calculation of average reservoir pressure and the productivity index done in the previous sections, we can easily back calculate the flowing pressure and the drawdown for each production nodes. The drawdown is the P between average reservoir pressure and the flowing pressure. that equals flowing rate divided by the PI. So for each production node, we know the flowing rate, we know the representative PI. Then we can easily calculate the drawdown at each production node, like this. Okay, if we look at the drawdown in the second quarter of 2023, the drawdown is nearly 600 psi. When the drawdown exceeds 6 psi, sand production begins to increase dramatically. So we assume the crucial drawdown pressure is as 600 psi. In well 7 case, it is recommended that the maximum flow rate is equals the representative PI times the crucial drawdown, that is 0.778 barrels per day per psi times 600 psi equals 467 barrels. This is the maximum flowing rate to avoid sand issues. So we need to decline the ESP frequency to make sure the flowing rate is less than 467. Otherwise, the drawdown exceeds 600. Then the sand producing would be an issue. Further application 2. Back calculate the strip and aquifer volume connected. In the material balance calculation, we need a representative average reservoir pressure, at least 3. Together with production data, it is possible to estimate the strip and the aquifer volumes connected. Using the representative average reservoir pressure and related the production data, with these numbers of the reservoir: porosity 23%, conic water saturation 0.26%, water compressibility using the default, formation compressibility 9E-6 per psi. We calculate the strip is around 22 million barrels. If without the aquifer, we would expect the reservoir pressure declined as this. So we can also calculate the volumes of the aquifer connected. The calculated aquifer volume is around 903 million feet. So this 3 point is the result of our calculation of average reservoir pressure. Field application 3. New wells development. New wells development. With the calculation of average reservoir pressure together with the production data and seismic data. Also with the result of the strip calculation. 3 new opportunities are identified. Here is the well number 9, well number 3, well number 5, well number 7. This is the producing formation. We also identified an opportunity here and 2 opportunities here. Away from the well number 9, the sound was good. The current reservoir pressure is higher because it's between well number 9 and aquifer. So we estimate well number 11, this one. We could get an initial rate at around 400 to 500. And the BSW expected from 2024 with a cumulative production exceed 300,000 barrels. Well number 12, we are expecting an initial oil rate at around 500 and it could last for 3 years. Expect the BSW from 2024 with a cumulative production more than 500,000 barrels per day. New well number 13. Initial pressure. The flowing pressure is around from 500 to 1,500. Initial production rate 450. It's close to the aquifer, so we are expecting a high BSW for this well. But the cumulative production here is also more than 400,000 barrels. So this is the main method calculating the representative average dynamic reservoir pressure and its application in the V field. So make a summary. First, we calculate the reservoir pressure and calibrate through the delta P per delta cumulative produced fluid, collect the necessary production data and build up data. Using this reservoir pressure build-up, we generate reservoir pressure profiles. Using this key value reservoir pressure profile, we can generate the dynamic reservoir pressure in a multi-well system. To get the initial average reservoir near the wellbores for other wells, we calculate productivity using the initial pressure, then calibrate the productivity index by the delta P per delta cumulative fluid. In this way, we found a representative PI for each well. Using the initial pressure, the representative PI, then we can back calculate the average reservoir pressure near the wellbores for simultaneously. Then we using this result, we have some applications to calculate the threshold drawdown, to avoid sand problem, to calculate the STOIP, standard original oil in place, and the connected aquifer volumes. And then using all of these results together with seismic interpretation, we found 3 new opportunities for the next development of the field. Thank you.